Hello, I'm Chris Fiatkowitz from the Department of Mathematics and Computer Science at Hobart and William Smith Colleges at Lakeside, Seneca, New York. I'll be discussing the browser-based neural axon simulator and visualizer developed with the assistance of Albright Dwarka and in collaboration with Tom Mortimer from the Department of Biomedical Engineering at Case Western Reserve University. This is a browser-based simulator, which means it's loaded and runs entirely in a web browser. It's available at anctoolkit.com, and it models a myelinated axon with an intracellular electrode and an extracellular electrode, and there are various plots and views available to look at the results of the simulation. The experiment settings involve a couple of settings for the axon itself, as well as stimulus settings for the intracellular and extracellular electrodes. Each electrode can apply pulses. A pulse is defined using a start time, a duration, and an amplitude, and each electrode can have as many pulses as you wish. And you can also configure the locations of the electrodes with respect to the axon. It's important to understand that the model is a computational model where we look at the nodes of Ranvier as membranes that can be modeled using electrical circuits based on the canonical Hodgkin-Huxley model, which includes potassium, sodium, and leakage currents. The Hodgkin-Huxley nodes are then combined for a full cable model using axial currents and an extracellular electrode potential, which can be understood for stimulation based on what's called the activating function, which I'll refer to later in one of the plots at the end of this presentation. The first plot we would usually look at, though, is the raster plot, which shows when action potentials occur. So in this plot, the vertical axis lists a node index, and I've run a simulation using 20 nodes numbered from 0 at the bottom to 19 at the top. The horizontal axis is time, and the markers in the plot indicate when the action potentials occur, that is, the peaks of the action potentials. And from this, we can look at the different behaviors that happen during the experiment. The membrane voltage plots show the membrane voltages of every node. I'm only showing 4 of the 20 nodes in my simulation in this case, but we can use this to dig down deeper and look at the effects of our stimuli. For example, when the extracellular stimulus was applied at 34 milliseconds in this simulation, we see there was a hyperpolarization on node 0, which affected whether or not this node would receive or exhibit an action potential at its regular time due to an intracellular stimulus. Additionally, we can drill down further into the model. Here's an example of looking at the channel gates for node number 3. In the Hodgkin-Huxley model, there are 3 channel gates, one of which, H, is the sodium inactivation, and we can study how this inactivation parameter was actually at a lower value than was necessary in order to normally achieve an action potential at the end of the cycle. Other views include looking at channel currents, such as sodium and potassium, and the activation function that is useful for understanding how neurons or axons are stimulated depending on where the extracellular electrode is, can be visualized using a plot that's available. Thank you for your attention, and there is additional information that you can find and features available at anctoolkit.com. I look forward to your questions.